With a huge round of applause, I would like to welcome the first speaker who will be addressing the first standalone session on the topic Agricultural on Mars. Please put your hands together and welcome Carl Henriksson. Carl is the Managing Director and founder of Henriksson Automate Limited, a UK-based engineering company and delivering advanced automated machinery solutions across the globe. With a decade of international experience in automation engineering, project management, PLC and HMI programming, and system integration, Carl has led diverse projects. Carl, over to you. Please put him a huge round of applause.
Thank you. It's so nice to be here. I was going to introduce myself, but he did a better job than me, I think. This photo is a few years ago. Never mind that. Okay, so I'm here to talk about agriculture on Mars. And the primary objective of this project is to create a symbiotic ecosystem in volcanic caves on Earth that can be recreated on Mars without the need for terraformation, by adapting to the conditions as they exist today. So by choosing the strongest organisms that can survive in extremely low atmospheric pressures and freezing temperatures, we can introduce single-cell organisms that provide the basic oxygen, biomass, and biofilms that can gradually give life to more complex organisms. So I'll get to that in a moment. So Mars may have had huge oceans of liquid water billions of years ago, but it was never in the habitable zone. So today I believe that Mars has reached the edge of the habitable zone, and the conditions are improving, and it can start to provide sustainable liquid water. It is currently not possible to grow plants on the primary surface of Mars due to the low atmospheric pressure, even if the surface temperature can reach above 30 degrees Celsius, because a warm climate is not sufficient. So the exception would potentially be the desert moss, which can tolerate extremely low pressures and high radiation and low temperature. But it would enter a dehydrated and a dormant state with a suspended metabolic activity. So it wouldn't be able to actively live or feed or reproduce. But there is a location which is a much more habitable, which is the Valles Marineris, which is a 4,000 kilometers wide canyon. And because it is 7 kilometers deep, at this depth, the atmospheric pressure is 3 times higher and reaches about 1,500 Pascal. So at these levels, it's possible for liquid water to exist on the surface, exposed to radiation, if the temperature is between 0 and 10 degrees Celsius before it evaporates. And there are many types of caves on Mars, but lava caves are the best habitats for life because of their geometry, temperature stability, and radiation protection. It is possible for them to obtain a stable temperature above 0 degrees Celsius, depending on various heat sources. So there's clear evidence that local geothermal heat, volcanic intrusions and magmatic sources are actively influencing the cave today. Sorry, not the cave, the canyon today. Volcanic caves can receive residual geothermal heat from lava flows by the conduction through solid rocks. Especially, sorry, I have to move forward. So, especially in the volcanic Noctis region in the west and the Kopert's Chasma region in the east. Right. So, so there's a lot of hydrothermal systems from magmatic sources which are associated with the shear zones. And any of these heat sources could heat up a cave by anywhere from 5 to 50 degrees Celsius or more. So we know that there's an abundance of water on the surface of Mars, and it exists in a permanent liquid form. So not just in sediments deep underground, but also in form of huge lakes and brines inside of caves. We believe that most of these brines will be too toxic to support marine life, but due to the primary chemical compound perchlorates. But there are perchlorate-reducing bacteria which could have eliminated the compound by converting them into oxygen a long time ago. So we should be able to find briny water with a low salinity and potentially even fresh water. It is absolutely necessary for a cave to have a large entrance in order for light to enter for the production of oxygen through photosynthesis. And this creates a challenge to create a high pressure inside a cave. Unless there's a presence of methane seep, then we can, that would generate a stagnation point that would prevent the flow of gas out of the cave. So normally a cave that is pressurized is completely sealed. But if it's shaped like a dome, then any gas produced could rise to the ceiling where it creates a local pressure while the surface pressure would equalize with the Martian atmosphere. But we would still have oxygen on the surface thanks to diffusion with CO2. So from light and water we have cyanobacteria, which is the basic building block for life on Mars. And cyanobacteria, I'm sure you all know what it is, but it is the only bacteria capable of producing oxygen through photosynthesis. So, and it only requires an additional source of CO2 and nitrogen gas and a few micronutrients. And it is capable of tolerating extremely low atmospheric pressures and freezing temperatures. And they're typically found by the cave entrances, and they can reach as far as an estimated 50 meters into a cave. Beyond this point, we have a far red light adapted cyanobacteria, which can be found deep inside caves. And by adapting to low light conditions, they produce a specialized, I believe it is a chlorophyll pigments that can capture far red light. In the absence of of light, we have a non-photosynthetic cyanobacteria, which can consume energy such as chemical compounds, such as hydrogen gas and nitrogen compounds dissolved in briny water. And they act as a primary food source, producing biomass and nutrients for other organisms. And they also create a biofilm that provides a protective surface for other microbes. In the absence of light, bioluminescence is essential because biogenic light can produce, it can provide photosynthesis for certain plants. And so we can introduce bioluminescent mushrooms, and it is a great organism because they lack vascular tissue found in plants, which so they don't absorb nutrients and water through any vascular tissue. And for that reason, they're capable of surviving extremely low atmospheric pressures while maintaining metabolism as long as the surface has some level of water. Bioluminescent cave worms are a type of insect in larva stage that become flying fungus gnats. And in the large colonies, they produce a significant amount of light, which would be sufficient to provide photosynthesis for certain plants. My mind is just frozen. Right. Oh, and this symbiotic relationship, I have not seen this anywhere on Earth before, and that is something that I would like to investigate and to change. The bryophytes, such as mosses, liverworts, and hornworts, are a type of non-vascular plants, and they don't have any leaves, stems, or roots to absorb water or nutrients, and they absorb them directly into their tissue. And this allows them to tolerate extremely low atmospheric pressures. Once the cave pressures have reached to 5,000 Pascal, or about 5% of the Earth's atmosphere, through the production of gas and the decay of living organisms, we can introduce vascular plants which can live in dark environments. So ferns have been chosen because of their tolerance to freezing and low levels of light, down to approximately 1% of typical daylight. The disadvantage is that they are highly susceptible to dehydration even at normal pressures. So in this case, we have the peace lilies and pothos, I hope I'm pronouncing that correctly, which are tropical plants, and they have thicker and waxier leaves which have better water retention. So once oxygen has been dissolved into the briny water and there's access to biomass, we can introduce complex marine life. And the advantage is that, and the reason why is because on Mars, the pressure increases by an estimated 3,700 Pascal for every meter of depth. So at 27 meters of depth, we would have 1 atmosphere of pressure, which is quite amazing, I think. So what you're looking at is bioluminescent dinoflagellates, and this type is called a Noctiluca scintillans. And They live on the surface of water, and they convert biochemical energy to produce a blue light, a blue-green light. In order to produce biogenic light in deep waters, there are the firefly squid, which are found in the deep waters of Japan. And they have specialized light-emitting organs called photophores, which produce light through biochemical reactions involving a compound called luciferin. The Vibrio fishery is a bioluminescent bacterium that lives symbiotically with other animals, such as the Hawaiian bobtail squid. And they are completely integrated into the tissue of their host. We can expand the ecosystem for a Martian briny aquifer cave for our symbiotic marine life by breaking down the ecosystem into 3 different groups: the filter feeders, detritivores, and predators. So the filter feeders extract particles, microbes from water, such as the brine shrimp that consumes free-floating microbes, and that forming the primary animal food source for the cave's predators. And glass sponges, they filter small particles and cleaning the surrounding environment. And fan worms, which are methanotrophic fan worms, they filter methane from liquid brines, and they host symbiotic bacteria. And detritivores, they move along the surfaces to consume organic waste and debris. For example, the sea cucumber. And there are the blind amphipods, such as the cave-dwelling crustacean. They lack eyes due to their dark environment, and they are scavengers and predators. Fungal mats. And this is the brackish water snail, and they're grazers of microbial and fungal films that derive energy from methane. And this is a cave salamander, and they're blind and adapted to total darkness that hunt shrimps and amphipods. In terms of equipment for an expedition to a lava cave, I would be using instruments that can be mounted on a drone that utilizes signal repeaters that can boost the radio frequencies, allowing us to control the drone from any point inside the cave, with the purpose of mapping the terrain, monitoring the growth of the organisms. In terms of transporting a cargo to Mars, we have SpaceX, for example, which is currently offering cargo shipments for $100,000 per kilo. So my suggestion is, instead of sending a scientist to Mars, we can send a humanoid robot that can be controlled from Earth. And if we select a Unitree R1, for example, that weighs just 25 kilo, that will cost $2.5 million to send out to the surface of Mars. But based on previous announcements, I believe that it can be far more affordable, down to $50,000 for such equipment. So that's all for now. That's all I had to say. That's my speech.
Thank you so much. There is one thing which we have always seen, and since this is the second edition of the AgriNext Conference, that the audience in the AgriNext Conference has been very interactive. So I would like to request anyone to please put your hands together for, put your hands up for having any questions. Do we have any questions to him? Yeah.
Congratulations, first of all.
Thank you.
Which technologies you identify that you're exploring to make agriculture in Mars that can help farmers here in the Earth? The train main.
So I think your question is how can my project contribute to agriculture, maybe both on Mars, on Earth? That is through the innovation into remote technology by investing in drones. And what I think moving away from standard procedures and I think, because I have not really seen much of it, attaching instruments to drones to measure the temperature and humidity, pressure, and so on. And actually, I wanted to say that I think we should look more into quantum technology, because we're getting to a point where we're not just limited to sending signals to Mars, limited to the speed of light, but that we can have zero latency. So I think that instead of continuously to deny that it's not possible to have two particles to change their state simultaneously, I think, because as an automation engineer, I specialize in digital technology, and I'm confident that it's possible to find some sort of algorithm that we can communicate with robots and our equipment on Mars with zero latency through this technology. And of course, by the end of this, when everything is finalized, when we do have a lot of life in our fresh or briny water, the idea is not just to look after them, but also to harvest, unfortunately, harvest these beautiful creatures for human consumption. So in this case, we maybe want to have an automated agriculture where we can automatically harvest these creatures, but also to provide them with some support.
Thank you.
Yeah.
Any other questions? Yeah.
Firstly, a well-made presentation gave us a lot of insight about Mars. Firstly, I'd like to ask, Chlorochlorochlocus, I think that is a very good cyanobacteria which will give you oxygen on Mars. That point is taken. But have we investigated phytoplankton that produces about 80% of the oxygen here on Earth? Any chance of growing phytoplankton on Mars?
Sorry, if there is a chance to plant it on Mars?
Yeah, to grow it the way we are investigating cyanobacteria on Mars. Any chance of, because phytoplankton produces 80% of the oxygen on Earth.
Yeah.
That's a very good investigation for us, where we can grow, have oxygen on Mars itself.
Yeah, no, like I said in the beginning, I think that instead of spending hundreds of years to try to transform the planet, let's do that procedurally. And let us just adapt to the planet instead. So there's nothing we need to do, any special procedure. We can grow cyanobacteria right now because the conditions are very favorable at that level on the surface of the Valles Marineris because of this 7-kilometer depth. But we might have to bring cyanobacteria with us if they don't exist. But I've looked into research material from professors and the European Space Agency, and I think it's quite clear that there is some geological activity there that's producing a lot of gas. And this is not just hydrothermal vents and methane seeps. I think this is being produced by bacteria actively right now. So what's happening is that NASA and SpaceX is on the wrong location. They're looking at the very surface, which is extremely hostile to anything organic. They can be in a frozen, dormant state, but they cannot live there. But they can on the floor of Valles Marineris. And that's why you see there's some stream of water, and then it goes away because the temperature at night drops to minus 70 degrees Celsius. That's why we have to start inside of a cave, because that's where we have temperature stability. And it's wishful thinking, the hope that it is 0 degrees Celsius. But with these additional heat sources that I presented, that is definitely realistic and achievable. And we might have to do some drilling to change the direction of, or the output of the methane seep, because it might not be located in a favorable place. You want to have it at the edge of the cave, so we can have that stagnation point. So the short answer is no need to make any adaptations.
Thank you so much. Please give him a huge round of applause.